Code Tether Radio, Episode 4, When Agents Fix the Agent System. Welcome back to Code Tether Radio. This is Episode 4, and today we are talking about a very particular kind of milestone, the day a network of local peer agents was used to debug and harden the system that is supposed to let agents do distributed work in the first place. The concrete task was simple to state and messy to execute. A GitHub issue had been assigned to codetether. The bot replied that it had picked up the issue. It said it had created a branch. It posted analysis. But when we looked for the actual branch, the commits, and the pull request, there was nothing useful there. No pushed branch with work. No pull request. No durable final result. The work had apparently entered the system, moved far enough to look alive, and then evaporated before delivery. That is the kind of failure that matters more than an ordinary bug. A normal bug says, this function does not work. A distributed work bug says, the whole promise of delegation is unreliable. If you cannot trust a remote worker to either complete the task or fail loudly, then you cannot offload work to it. You can only babysit it. And babysitting is the opposite of automation. So the headline of this episode is not only that we fixed a GitHub Action runner and an API job processing path. The bigger story is that we used codetether's own peer agent protocol to do it. 3 local agents running as separate processes, reachable over A2A endpoints on a local machine and local network, collaborated on one reliability problem. One agent coordinated. One agent owned the GitHub Action repository. One agent owned the API and server side. They exchanged messages over A2A, accepted tasks, reported status, got stuck in some places, recovered in others, and ultimately produced concrete pull requests. That is the important part. We did not simulate collaboration inside one large prompt. We used separate agents, separate repositories, separate working directories, and a protocol boundary. This was real peer-to-peer agent work in the small.
Let's start with the architecture that made it possible. In codetether, an A2A peer exposes an agent card at .wellknown/agent.json, and it accepts JSON RPC calls on the root path. The server implementation routes methods like message/send, message/stream, tasks/get, and tasks/cancel. The agent card says what the peer is, what skills it has, what URL to call, what protocol version it speaks, and whether it supports streaming and task history. In the code, that is not a vague idea. The A2A server creates routes for the agent card and the JSON RPC handler. The handler dispatches message/send, message/stream, tasks/get, and tasks/cancel. The default card describes codetether as an A2A native AI coding agent with code generation, debugging, and explanation skills. The discovery layer is equally concrete. Codetether has an MDNS module that announces services under the service type _codetether-a2a._tcp.local. The MDNS record includes TXT fields like name, path, protocol, and version. The spawn path binds the TCP listener first, because if you are using port 0, you cannot publish a URL until the operating system tells you which port was actually assigned. Then it derives a public URL, builds the agent card, registers the card on the local bus, announces readiness, starts explicit peer discovery if seed peers were configured, and starts MDNS announce and browse if enabled. There is also a Linux caveat that mattered in our earlier discovery session. MDNS multicast does not reliably traverse the loopback interface on Linux because loopback typically lacks the multicast flag. So 2 peers, both bound to 127.0.0.1, may be reachable by direct HTTP, but not discover each other through MDNS. The code comments say the reliable single host pattern is to bind 0.0.0.0, so announcements go through the real interface. That distinction matters because our peer agents were reachable locally by their ports, and their cards advertised LAN URLs, but discovery itself has practical network constraints. This is the kind of detail you only see by reading the code and touching the system.
During the collaboration, the coordinator had previously found peers like the codetether-action agent and the A2A server MCP agent by querying their agent cards.
Those peers had names like Ubuntu-dev-codetether-action and Ubuntu-dev-A2A-server MCP. They were not magical personas in a shared chat. They were processes with HTTP endpoints. We spoke to them using A2A JSON RPC. When the task was too long, we learned that message/send could block or time out. So we used message/stream and tasks/get. That was not just a convenience. It was a lesson in the shape of agent reliability. Long-running work needs task IDs, status polling, partial progress, and terminal states. The first concrete mistake was ours. The user pointed us at issue 105, and we fixed the issue itself. That issue was about the training bus. V2 training records had dropped agent_thinking records and lacked model attribution, provider attribution, usage metrics, and schema versions. We created a codetether-agent pull request that added schema version 2.1 metadata, model info and usage info on bus envelopes, model and provider fields in training records, token usage metadata, a config gate for agent_thinking records, and documentation for the training record schema. That was useful work, but it was not the real fire. The user stopped us and said, in effect, yes, the training issue is real, but look at the comments. The GitHub Action agent had already been asked to fix it. It claimed the task, posted analysis, and failed to deliver. That was the actual platform problem. The distributed worker was brittle. This is a subtle but important distinction. In human terms, if a teammate says, I am on it, and then nothing happens, you have a coordination problem. In agent terms, if an automated worker says picked up, creates no verified work product, and the system has no reliable failure signal, you have a protocol and lifecycle problem. The issue is not merely that one agent made a bad patch. The issue is that the surrounding system allowed partial progress to masquerade as useful work. So the task shifted. We needed the agents that owned the relevant systems to inspect their own repositories. The codetether-action peer was asked to investigate the GitHub Action runner, action.yml, entry point scripts, server mode, local mode, failure propagation, branch pushes, pull request creation, logs, and artifacts. The A2A server MCP peer was asked to investigate the API and job processing side, task dispatch, worker lifecycle, terminal hooks, status transitions, timeouts, final issue comments, branch and pull request verification, and audit trails. This is where the protocol mattered. The coordinator did not open those repositories and manually do all the work. It delegated across A2A. The messages were direct, structured prompts sent to peer endpoints. The peers responded as agents with their own task IDs and working states. When one path timed out, the coordinator changed strategy. When streaming returned a task ID but no incremental artifacts, the coordinator used tasks/get. When a task appeared stuck, the coordinator sent a smaller follow-up task. This was not perfect. It was an honest, distributed systems experience. Some calls completed, some calls timed out, some tasks stayed in working, and smaller messages worked better than broad, monolithic ones. That imperfection is part of the story. A peer protocol does not automatically make agents reliable. It gives you the handles you need to build reliability: identity, endpoints, task IDs, streaming, polling, artifacts, and final states. But you still have to design workflows that use those handles well. The API-side agent produced the first major result. It found that the hosted worker path was missing important terminal behavior. There was already a worker SSE path that called a GitHub app terminal task hook on completion, but the hosted worker path did not call the same hook. That meant a job could finish internally but fail to post the final GitHub issue comment or pull request link. To a user watching GitHub, the task would look abandoned. The API-side agent also found that the task state model was too coarse. Jobs could jump from queued to running to completed or failed, but there was no durable representation of intermediate states like picked up, pushed branch, or opened pull request. Without those states, you cannot tell whether a job died before being claimed, died while executing, pushed a branch but failed to open a pull request, or completed but failed to notify GitHub. Every one of those cases has a different operational response. The fix became a pull request in the codetether repository, pull request 53. It added durable job lifecycle states, such as picked up, pushed branch, and opened PR. It added a state transition validator. It introduced a task status audit module and a database migration for a task status audit table. It changed the hosted worker so completion calls the GitHub app terminal hook. It added branch and commit verification before posting final issue comments. It also fixed a concrete runtime bug. A started at variable was local to one method but referenced in another method, which could cause a name error in the completion path. The fix promoted started at to an instance attribute, so completion and audit metadata could access it safely.
That pull request then received review comments, and the agent handled those too. Reviewers caught an unbound local error risk around task ID, a JSON-B parsing issue where async PG may already return a dictionary instead of a string, an unused import, a redundant timestamp because the database already had a default, a pool injection concern, a lifecycle docstring omission, long lines that could bother rough, and a misleading variable called commit count when the code was really checking whether commits existed. The agent pushed a follow-up commit addressing all of that. It ran targeted Python tests, GitHub app mention tests, task orchestration tests, and hosted worker dispatch sync tests. 9 tests passed. On the action side, the first big task itself demonstrated the brittleness we were trying to fix. The codetether-action peer accepted a long reliability task and remained in a working state without useful progress artifacts. That was frustrating, but it was also diagnostic. Long tasks that do not produce progress are exactly the failure mode. The coordinator then sent a smaller, minimal action side task: implement guardrails, capture logs, fail closed, verify branch push, verify pull request creation, and surface failure comments. That smaller task completed and produced a pull request in the codetether-action repository, pull request 1. The action side pull request changed a runner from optimistic to fail closed. Before the fix, server mode could effectively hardcode a successful exit even when the underlying task failed or timed out. Local mode could swallow the codetether binary's failure. Push operations were not verified. A branch or pull request could be assumed instead of proven. The new action behavior is much more explicit. The action captures logs to a persistent file. It uploads artifacts even when the workflow fails. It records dispatch responses, task result text, codetether output, prompts, and diff patches. It adds a fail on error input, defaulting to true. It exposes the server task ID as an output. It writes a GitHub step summary at every exit path. It posts picked up comments and failure comments. It verifies that a pushed branch exists on the remote. It verifies that the expected commit SHA is actually at the branch tip. It adds helper functions for creating pull requests with retry and duplicate detection. In other words, it stops treating good intentions as results. That action pull request also received reviewer feedback. Gemini Code Assist and Copilot flagged curl standard DAR leaking into response parsing, defensive response file handling, shell exit code capture bugs after negated commands, a JQ guard in commit verification, an invalid GitHub step summary environment mapping, and oversized log embedding in step summaries. The action peer addressed those comments in a follow-up commit. It redirected curl standard DR into logs, added empty fallbacks, fixed exit code capture, guarded JQ access, removed the invalid end mapping, and truncated embedded logs. It ran bash syntax checks on all changed shell files. This is the practical accomplishment. We did not just patch one bug. We moved the system toward a contract. If an agent says it picked up work, the platform must eventually show one of a small set of verifiable outcomes. It opened a pull request. It pushed a branch and could not open a pull request with a reason. It failed with logs. It timed out with a task ID and enough state to debug. It did not vanish into a comment thread. Now, let's step back and talk about why the peer agent protocol matters more than the specific code changes. A single agent with a single giant context can do impressive work, but it tends to blur ownership. It can inspect any repo it can reach, make guesses about systems it does not own, and produce a monolithic answer. But software systems are not monoliths. The GitHub Action repository has shell scripts, action metadata, workflow artifact behavior, and GitHub CLI semantics. The API repository has Python workers, database migrations, task queues, GitHub app hooks, and task status semantics. The codetether-agent repository has Rust A2A protocol code, local bus code, session handling, and training data capture. Different parts of the system benefit from different local contexts. Peer agents let those contexts stay separate.
The action agent can live in the action repo. The API agent can live in the server repo. The coordinator can delegate, pull, and summarize. Each peer has its own local tools, current working directory, history, and repository assumptions. That is much closer to how human engineering teams work. You do not ask one person to keep every repository in their head forever. You ask the person closest to the system to investigate and produce a patch.
The protocol boundary also forces healthier communication. An A to A peer is reached through an agent card and JSON RPC methods. The coordinator sends a message. The peer returns a task. The coordinator can pull that task. The response includes status, history, artifacts, and final messages. This is not a magical shared context. It is a distributed workflow. That distinction is valuable because distributed workflows can be observed, tested, retried, and improved. In the code, the A to A server stores tasks in a dash map. When message/send arrives, it creates a task with a working status, records the inbound message, extracts prompt text, and either runs synchronously for blocking calls or spawns background execution for non-blocking calls. It emits A to A inbound and outbound events onto the local bus as agent message records. It records telemetry for A to A messages, including duration, success, output, and errors. The client side has methods to fetch an agent card, send a message, get a task, cancel a task, and make JSON RPC calls. These are the primitives we used in practice. The local bus adds another layer. Bus envelope carries topic, sender ID, correlation ID, timestamp, and the bus message payload. It now also has optional model info and usage fields from the training bus work. Bus message includes lifecycle events, direct agent messages, task updates, artifact updates, shared results, tool requests, tool responses, full tool output, heartbeats, and agent thinking. So there is a local event fabric underneath the peer endpoints. A to A messages are not isolated HTTP calls. They can become bus events, telemetry, training records, and UI visible activity. That is why Episode 3 focused on MDNS and peer discovery, and Episode 4 focuses on collaboration. Discovery is how peers find each other. Collaboration is what happens after they are found. In our case, we had enough reachability to message the peer agents directly. The next step is making the collaboration itself robust, streaming that actually streams progress, task/get that reports meaningful state instead of repeating the initial prompt, artifacts that summarize intermediate work, and terminal states that cannot lie. The interesting thing about this session is that it exposed reliability problems at two levels. At the product level, the GitHub Action worker claimed work but did not deliver a branch or pull request. At the peer protocol level, a long delegated A2A task could sit in working without useful progress. Both are versions of the same failure. Distributed work needs observable progress and trustworthy terminal states. If the protocol says working forever, that is not enough. If GitHub says picked up but there is no branch, that is not enough. If a workflow exits 0 after a failed server call, that is actively harmful. So the theme becomes agents need receipts. A receipt is a task ID. A receipt is a branch name that exists remotely. A receipt is a commit SHA that matches the expected branch head. A receipt is a pull request URL. A receipt is a final issue comment. A receipt is an artifact log uploaded even on failure. A receipt is a database row in a status audit table. A receipt is a state transition from picked up to running to pushed branch to opened PR. A receipt is a failure comment with the workflow run link. Without receipts, an agent system is theater. With receipts, it becomes infrastructure. This is especially important for offloading work. The user said they need to offload more work to the action. That means the action cannot be merely impressive when watched, it has to be reliable when ignored. A reliable worker must fail loudly, preserve evidence, and make forward progress verifiable. It should not require a human to inspect logs just to know whether anything happened. It should present the outcome in the place where the work was requested. That is why the action side changes matter. A GitHub action is the user's bridge between an issue comment and an automated engineering attempt. If that bridge exits successfully after a failed server pull, the whole system lies. If it cannot verify that its branch push reached GitHub, it is guessing. If it creates no artifact logs, failure analysis starts from 0.
If it cannot post a failure comment, the user has to hunt through workflow runs. The fix turns these silent edges into explicit edges. The API side changes matter for the same reason. A server that only knows queued, running, completed, and failed cannot explain enough. Was the worker claimed? Did the branch push happen? Was the pull request opened? Did the final GitHub hook run? Did audit logging fail? Durable status transitions let operators and agents reason about where a job is. The audit trail makes the history queryable. The terminal hook ensures hosted worker completion reaches the GitHub surface.
There is a broader design lesson here. Multi-agent automation should be treated as a distributed system, not as a longer prompt. Distributed systems need idempotence, retries, durable state, timeouts, observability, and explicit failure modes. Agents do not exempt us from that. They make it more urgent because their failures can be semantically subtle. An agent can write an excellent analysis comment and still fail the task. The system must distinguish analysis from delivery. This is where peer agents become valuable beyond parallelism. A peer can notice another peer's failure mode. The coordinator noticed that the action peer's long task was stuck. It changed the task shape. It used a smaller prompt. It verified the repository state with Git and GitHub. It did not simply trust the peer's final text. That is a pattern we should build into the platform. Peer coordination should include independent verification. Imagine a future code tether workflow where a coordinator assigns a bug to a worker. The worker reports that it created a branch. A separate verifier agent checks the remote branch. The worker reports that it opened a pull request. The verifier checks the PR URL, base branch, head branch, and commit SHA. The worker reports tests passed. A test agent checks the logs or reruns a targeted suite. The coordinator summarizes only verified facts. That is the direction this session points toward. The local network aspect matters because these agents were nearby. They were not faceless cloud invocations behind one API. They were local or LAN-reachable peers with agent cards and endpoints. Locality changes the operational feel. You can run an agent in the action repo, another in the API repo, another in the agent repo, and coordinate them through A to A. You can inspect their cards. You can query their ports. You can send messages. You can pull tasks. You can route work according to repository ownership. This is the practical form of an agent fabric. It is not yet a perfect swarm, it is not yet fully autonomous, it is not yet self-healing, but it is real enough to expose real failure modes and produce real pull requests. There was another lesson in the review phase. The peer agents did not just produce first-pass patches, they also responded to reviewer feedback. The action peer addressed shell-specific issues that reviewers caught: curl STDR, bash negation exit codes, JQ guards, summary size. The API peer addressed Python and database issues: JSON B decoding, unbound variables, pool injection, formatting. That matters because collaboration is not just task dispatch. Collaboration includes review loops. A useful agent has to survive feedback and narrow its changes to the review comments. The reviewer phase also validates the value of specialization. Shell scripts have their own traps. Capturing exit codes after negated commands is a classic bash pitfall. Curl can write progress or errors to standard error and contaminate parsing if not isolated. GitHub Actions has special environment files like GitHub step summary that should be used by path, not passed as an ordinary env mapping. Meanwhile, Python async PG JSON B behavior is a different domain. Database defaults, optional pool injection, and state machine docstrings are not shell concerns. Separate agents working near their domains made the feedback easier to address. The result is two complementary pull requests. The action pull request makes the runner honest and observable. The API pull request makes job processing more durable and visible. Together, they close the loop that failed on issue 105. If the same kind of task is assigned again, the system should be much more likely to either produce a verified PR or tell the user exactly why it could not. But let's not overstate. The peer protocol still showed rough edges. The first long action side task did not give good progress. Task/get repeated the initial prompt rather than reporting useful intermediate artifacts. Message/stream returned a working task object but did not stream rich incremental text. That is not a reason to dismiss the protocol. It is a roadmap.
The next improvements are obvious. Agents should emit progress artifacts during long work. Task/get should surface latest checkpoints, not only the submitted message. Streaming should be used consistently for lull-running operations, and coordinators should break large assignments into smaller, verifiable tasks. This is exactly how infrastructure matures. You use it on a real problem, it fails in specific ways, you harden the specific edges. Then you use it again. One of the most important shifts is from trust to verification. Early agent demos often rely on trust. The model says it did the work, so the transcript looks done. Engineering cannot stop there. We need branch existence checks, commit SHA checks, pull request checks, test result checks, artifact uploads, failure comments, status audits. Those are boring in the best possible way. Boring is what makes automation reliable.
And there is a philosophical point hiding in the plumbing. Agents are going to collaborate, not because they are charming conversationalists, but because they can share responsibility through protocols. A protocol lets one agent say, here's a task. Another agent says, here is a task ID. Later, it says, here is a branch and a pull request. Another system says, here are review comments. The agent says, here is the follow-up commit. The coordinator says, here is the verified summary. That chain is more important than any single message. This episode is called When Agents Fix the Agent System, because that is what happened. The system for distributed agent work failed to complete distributed agent work. Instead of only fixing the original issue by hand, we used the peer agents to harden the path. The action agent fixed the action. The API agent fixed the API. The coordinator kept the agents moving, verified their outputs, and summarized the result. That is a small but meaningful self-improvement loop. Not recursive magic, not a fully autonomous research lab. A practical loop. Observe failure, delegate to owners, patch the workflow, handle review, verify pull requests. What should listeners take away? First, A2A peer agents are not just a demo feature. They are useful for routing real engineering work to the context that owns it. Agent cards, JSON RPC, message/send, message/stream, task/get, and local discovery are enough to build meaningful collaboration patterns. Second, local network collaboration matters. When agents run near the repositories and services they own, they can act with better context and clearer boundaries. MDNS and LAN discovery are the bootstrap. Direct endpoints and task IDs are the working surface. The local bus and telemetry provide observability beneath that. Third, distributed agent work must be designed like distributed systems work. You need durable state, terminal hooks, retries, audit trails, artifacts, timeouts, and explicit failure propagation. If a worker can silently fail after posting a confident comment, the platform is not ready for serious offloading. Fourth, peer collaboration should include verification. Do not let the same agent that claims success be the only source of truth. Check the remote branch, check the commit, check the PR, check the tests, check the review comments. This is how agents become trustworthy teammates rather than eloquent guessers. Finally, the work is iterative. The protocol worked well enough to coordinate real fixes, and it failed visibly enough to show what to improve next. That is success. A brittle system that hides failure is dangerous. A system that exposes brittleness gives you the chance to harden it. So episode 4 ends with a more grounded vision than episode 3. Episode 3 said local agent discovery is the future, because agents need to find each other. Episode 4 says peer-agent collaboration is the future, because once agents find each other, they can divide responsibility, fix the tools they use, and create verified work products across repositories. The future is not one giant agent doing everything. The future is a fabric of agents, with names, cards, endpoints, tasks, logs, branches, pull requests, audits, and receipts. The future is not an agent saying, trust me. The future is an agent saying, here is the PR, here is the commit, here are the tests, here are the logs, and here is the status history. That is what we built toward in this session. We fixed the training issue. We discovered the deeper reliability issue. We coordinated peer agents over A2A. We produced an API-side reliability pull request.
We produced an action-side reliability pull request. We handled reviewer feedback on both. And we learned in practice that the same protocol that lets agents collaborate also reveals where collaboration needs stronger guarantees. Thanks for listening to Code Tether Radio. This was episode 4, When Agents Fix the Agent System. Next time, we will keep following the trail from local peer discovery to durable, trustworthy, multi-agent software development. The dream is not just agents that can code. The dream is agents that can coordinate, prove their work, survive review, and improve the system they depend on. Before we close, there is one more practical detail worth naming. This whole session changed the meaning of an issue comment. At the beginning, a comment that said "picked up" sounded reassuring. By the end, picked up became only the first state in a life cycle. That is a huge shift. A status comment is not a delivery guarantee. It is a promise that the system now owes the user more evidence. That evidence can be automated. When the action starts, it can comment with the task ID and workflow run. When the server accepts the work, it can record picked up. When the worker creates a branch, it can record the branch name. When it pushes, it can verify the remote ref. When it opens a pull request, it can record the PR URL. When reviewers comment, it can capture those comments as follow-up tasks. When it fails, it can write the reason into GitHub and preserve logs as artifacts. Every step gives the user and the next agent a better handoff. Thanks for listening to Code Tether Radio. This was episode 4, When Agents Fix the Agent System. Next time, we will keep following the trail from local peer discovery to durable, trustworthy, multi-agent software development. The dream is not just agents that can code. The dream is agents that can coordinate, prove their work, survive review, and improve the system they depend on. Before we close, there is one more practical detail worth naming. This whole session changed the meaning of an issue comment. At the beginning, a comment that said "picked up" sounded reassuring. By the end, picked up became only the first state in a life cycle.
This is also how agents become composable. A verifier agent cannot verify a vague feeling of progress. It can verify a URL, a SHA, a status row, a workflow artifact, or a test report. A coordinator agent cannot intelligently retry a black box failure. It can retry a specific failed transition. Maybe branch creation succeeded, but PR creation hit a duplicate. Maybe PR creation succeeded, but final comment failed. Maybe tests failed, and the worker should fix the test output. The more specific the state, the better the next action. In human teams, we often learn this through incident response. Someone says, the deploy worked, but customers are still broken, so we add health checks. Someone says the job finished, but the output file is missing, so we add output verification. Someone says the notification sent, but the receiver never saw it, so we add delivery receipts. Agent systems need the same operational maturity. The fact that the worker is powered by an LLM does not change the fundamentals. If anything, it means we should be stricter, because language can sound complete even when the system state is incomplete. There is a useful mental model here. Every agent claim should eventually bottom out in a non-linguistic fact. Not because language is bad, but because software delivery is stateful. A claim like, I opened a pull request should bottom out in a pull request number and URL. A claim like, I pushed a branch should bottom out in a remote ref and commit SHA. A claim like, tests passed should bottom out in a command, an exit code, and logs. A claim like, I could not complete should bottom out in an error class, a failed transition, and a preserved artifact. The words are the interface. The receipts are the trust. This is where CodeTether's bus, training records, and A2A work begin to connect. Training data without model attribution and usage is less useful, so episode 4 also touched the training schema. Agent collaboration without task receipts is less useful, so the action and API pull requests added receipts. Pure discovery without stable task semantics is less useful, so the next protocol work is richer task progress. These are not separate concerns. They are all parts of making agent work legible. Legibility is the underrated requirement. If an agent acts but no one can tell what happened, the action has little operational value. If an agent fails but the failure is hidden, it creates risk. If an agent succeeds but the success cannot be verified, it still requires manual trust. The goal is to make agent work legible to humans, to other agents, and to automation.
which means structured state, readable summaries, durable logs, and machine-checkable references.
A local peer network is a perfect place to develop that discipline. You can iterate quickly. You can run one peer per repository. You can inspect ports, cards, task states, and pull requests. You can learn which prompts are too large and which task boundaries produce useful artifacts. You can watch a peer get stuck and then design a smaller task that succeeds. You can discover which status fields are missing because you actually need them during coordination. That was the hidden value of the session. The agents did not merely complete assignments, they taught us what the assignment system itself needs. The action needed fail-close behavior. The server needed terminal hooks and audit states. The A2A task flow needs better progress surfaces. The coordinator needs verification patterns. Each pain point became a design requirement. And that is why this feels different from an ordinary coding session. In an ordinary coding session, we might end with a diff. In this one, we ended with a stronger workflow. We ended with 2 pull requests, yes, but also with a clearer doctrine. Distributed agents must produce durable, externally checkable evidence of their work. Peer agents should own their local domains. Coordinators should verify claims. Long tasks should stream progress or split into smaller tasks. Terminal states should mean something. If codetether keeps following that doctrine, then offloading work stops being an act of faith. It becomes a queue of observable, auditable, reviewable engineering attempts. Some will succeed, some will fail, but the system will tell us which, where, and why. That is the foundation we need before scaling from a few local peers to major agents across machines, repositories, and organizations.